Hello and welcome to part 3 of my explanation on Gödel's Incompleteness theorem. So, what we're going to try to do here is take what we learned last time about the propositional calculus and apply it to number theory. Number theory might be a bit of a vague notion, but the idea here is that what we're worrying about is the natural numbers 0, 1, 2, 3, and so on. Well, if you look at what we've done, our first video all we did was take an axiom, apply rules to it, and then we got theorems. Then last time we also found that the symbols we choose to spell our axioms with based on the rules can actually give it a passive meaning. What we are trying to do is give passive meaning to the symbols we choose to use that will correspond to statements of number theory. And our ultimate goal would be to have the theorems be true statements and the non-theorems be false statements. The first step is we should make sure we can express all statements of number theory using nothing but a few symbols. And then the hard part, we have to figure out what rules we can use to give those symbols that we've chosen to use the correct meaning. Why would this be so excellent if we could do it? Well, essentially, we wouldn't have to worry about unsolved problems in mathematics anymore. We could just check if a statement of number theory was a theorem, and if it is, there we go, we've got a true statement, and if it's not a theorem, well then we've got a false statement. And naturally, typographical rules are much easier to work with than properties of numbers. I've got a few statements of number theory here. We're going to see if we can translate them into symbols, and if so, how many symbols do we need? 5 is prime, 2 is not a square, and by square I'm referring to square numbers. 1729 is a sum of 2 cubes. No sum of positive cubes is itself a cube. There are infinitely many prime numbers, and 6 is even. Looks like we've got a lot of concepts. Maybe prime, square, cube, infinity, even. 5, too, we need all the numerals, but it turns out we can define these properties in terms of much simpler notions. For instance, statement 1, I've marked it statement 1 prime here. You'll recognize that mode of thinking from our last video. The sentence 5 is prime could also read, there do not exist numbers a and b both greater than 1, such that 5 equals a times b. 2 is not a square. Can easily be read, there does not exist a number b such that b times b equals 2. We've already figured out how to talk about squares, so talking about cubes is the same thing, we just add another times c. So statement 3 is fairly trivial. No sum of positive cubes is itself a cube. For all numbers b and c greater than 0, there is no number a such that a times a equals b times b times b plus c times c. On the fact that there are infinitely many prime numbers, how are we going to say that? What we can say is that for each number a, there exists a number b greater than a with the property that there do not exist numbers c and d both greater than 1 such that b equals c times d. And then 6 is even is back to very simple. There exists a number c such that 2 times c equals 6. So let's get to actually deciding what notation we're going to use. Naturally, we will need numerals. The symbol we'll choose for 0 is the familiar one. We'll put an s in front of each successively larger number. You can think of s as meaning the successor of. 1 is the successor of 0. 2 is the successor of 1. For variables, we'll use the same sort of system we did when talking about atoms of the propositional calculus. We'll do a through e and then add primes. We might be getting ahead of ourselves a little bit here, but we're going to talk about what constitutes something called a term that we'll need quite often once we're learning how to actually construct this system. We're using familiar symbols for both of these concepts. So the way we define a term, numerals and variables are all terms, and any term that has an s in front is also a term. Then if we have any term s and t, then s plus t in the parentheses and s times t are also both terms. I've just got a few simple examples here. So terms can be as short or long as you want them to be. Now that we know what terms are, it's time to talk about atoms. You'll remember from the propositional calculus that atoms are the smallest type of well-formed string. The same's going to turn out to apply here, but let's see what we define atoms as, because it's very different than what we did last time. What we're going to need are two terms, s and t, and if we have both of those, then s equals t is going to be our atom. The next type of symbol we're going to need are called quantifiers. You'll remember from the sentences that we ended up with, there was quite often that we said there exists a number blank such that, or for all numbers blank. To use quantifiers, we need what we're going to call a free variable. This sentence, even though you can see that the sort of English translation is a prime equals 1, it's still called a free variable because it doesn't have a quantifier attached to it. And finally, we're going to need to borrow some stuff from the propositional calculus. Actually, we're going to borrow everything from the propositional calculus, except what we used as atoms there, we're going to replace with what we called atoms here. So we're going to use what we know so far to make this well-formed string. Just taking what we had there and putting the not in front of it. Certainly the fact that this happens to be a false statement doesn't make it less well-formed, though it will make it not a theorem. Now we're going to see if this kind of massive thing is going to turn out to be well-formed or not. You'll remember we needed a well-formed string on both sides of this symbol, and certainly it looks like those are both well-formed, but there's a problem here. First, this is not an atom. We need to have an equal sign for it to be an atom. What we have here is just a term, which isn't large enough to be a well-formed string. So, we're gonna take this part here that came after this, and we're just gonna tag an equal sign and something quick. But there's also another problem. We're not allowed to have a variable that is quantified on one side and free on the other side, and that's the situation we have with a prime. So we're taking this first fix, and we're gonna add another fix to it. It's important to remember that the concept of being well-formed does not mean true. It can be a false statement, but it needs to be intelligible. Anything that's not well-formed is also not going to translate well into English. Like, for instance, here, we'll say that if we assume that there isn't a value for a prime such that 1 equals a prime, then we can infer that the number after a prime times 0 plus the number after a prime times the number after 0, and that's the whole thing. You can tell there's something missing there. That wasn't a sentence. Translation doesn't make any sense. And then, perhaps a little cumbersomely, this means that if we assume that there's no value for a prime, such that a prime is going to be the number after 0, then we can conclude that for all values for a prime, this is going to be a true statement, and it's just a statement of equality that's long and silly and clearly false. But that's okay. It makes sense. We've got a full statement in English here. And now, in fact, we have a series of symbols that we have just artificially added passive meaning to, and it's going to be good enough that we can translate our sample sentences. I've skipped around on the order a little here just so that I can introduce concepts more simply. We'll start with number 2, which sentence in English was 2 is not a square. Know that there is not a value for b such that b times b equals 2. That's true, and that's certainly a good way to say it. 6 is even, which when we put it in this notation, we get there exists a number e such that 2 times e equals 6. And you'll notice, it doesn't really matter what side of the equal sign which part goes, or even which way we do the multiplication. Each of these 3 strings is different. Just because we know in our heads that they all mean the same thing does not mean necessarily that if we prove one of them, then we've proven all of them. Of course, as it turns out, we will be able to make it so that all of those three interpretations are theorems. 1729 is a sum of two cubes. Unfortunately, 1729 is a large number, and I was certainly not about to write all of those s's out. So we have, there exists a b and a c, such that this large number, which is 1729, equals b times b times b, plus c times c times c. However, there are ways to say this that don't involve writing that gigantic number of s's. Now, our statement, no sum of positive cubes is itself a cube. What we're saying is, for all values of a, there does not exist a b or a c such that a times a equals... Well, why did I put the successor of b? Know that 0 times 0 times 0 does equal 0 times 0 times 0 plus 0 times 0 times 0. So in order to get around that interpretation for b and c, which would be valid, we'll put an s in front of them. So even if we say b and c are both 0, then we've still got 1 times 1 times 1 plus 1 times 1 times 1. And now that we have that trick, we can see how we can even talk about primes. Since sentence 1 was 5 is prime, what we're saying here is there do not exist numbers b and c such that 5 equals the successor of b times the successor of c. There are infinitely many prime numbers. For all values d, there exists a value e, but there do not exist b or c such that d plus the successor of e equals b when b is at least 2 times c when c is at least 2. So that means that there is a prime number that is larger than d because we're adding something non-zero to it. So far we've had success. We see that we've found a group of symbols where the well-formed ones are sensible statements of number theory and all the non-well-formed ones are nonsensical. And we need to know that every single rule of the propositional calculus also applies here. But that won't be sufficient. We'll need some new rules. If we take a look at the axioms, though, we see that when interpreted, these do make fairly basic statements. This one is giving 0 a special property. It says that no matter what you use for a, the successor of a is not 0. Now these two are properties of addition. Now for multiplication, we start out with a times 0 equals 0. Nice basic fact. And then this one talks a little bit about the relationship between multiplication and addition. Now for the rules, we're going to be using some notation that you can see isn't valid within TNT. Also, we're going to be referring to this system as TNT for typographical number theory. We see in this notation that x is going to be a string, and u is going to be a variable within x, this string. And our first rule, the rule of specification. If, for all values of a variable, then x is a theorem, then so is x. And so are strings made from x by replacing u with one term. So how do we use this? Let's take Axiom One, which is for all numbers a, it's not true that the successor of a equals 0. So we've got a variable here. Let's replace that variable with a term. You can see that is still a true statement, or we could be a little more complicated and say that instead of a, we're going to write c plus 2. And so this is also a theorem. Then our rule of generalization is going to be the opposite. If we have a string x that's a theorem, and u is a free variable that's in x, then we can have for all values u, then x, and that is also going to be a theorem. Our next rule will be the interchange rule, which is that if we have any variable, and all instances of that variable mean that not something or other, we can exchange it with there does not exist a value for whatever variable such that whatever. And this one actually goes backwards as well as forwards. You can use either of these two interchangeably. And since axiom number 1 has the nice beginning that we have here, let's use that as an example. For all values a, not the successor of a equals 0. And so we can naturally also say that there does not exist a value for a such that the successor of a equals 0. The next rule is the rule of existence, which says that any term within a theorem may be replaced by a non-occurring variable. With the addition of the quantifier, there exists a value for the new variable. And since axiom 1 of course contains terms, let's use that. Let's take this numeral 0 here as the term that we're going to use the existence rule on. Let's replace it with the variable b. And then we have to add this quantifier, there exists a value b. The rule of symmetry is pretty simple. If r equals s is a theorem, then so is s equals r. Then there's the rule of transitivity, which is another thing we'll be familiar with. If r equals s and s equals t, then r equals t. Then there's the add or drop s. If r equals t is a theorem, then so is the successor of r equals the successor of t. And then the reverse is true as well. Now, you might think that such a very lofty goal as a system that's going to be able to sort out all true statements of number theory from all false statements of number theory would need to be much more complex. But it turns out we're actually almost done. Let's take an example. And a very simple statement of number theory, 1 plus 1 equals 2. We want to be able to see that this is a theorem since we know it's a true statement. First, let's translate it into our notation. So we've got 1 plus 1 equals 2. Very easy to translate. Very nice. Every time a appears here, we're going to replace it with the numeral for 1. Since we know the specification rule, we know this is going to be valid. Now let's specify for b as well. And instead of these b's, we're going to write our numeral for 0. Now, if all we're thinking about is the English translation, then it doesn't matter, we're already there. 1 plus 1 equals the number after 1, which is 2. But we've already decided that we need to make sure that this specific interpretation, since we know it is a valid interpretation, is right. So for all values a plus 0 equals a. Let's specify for a, and we're going to use 1 again. And we know we can add s, we're going to add s to both sides. And look here, we have this term, which appears right here, and it also appears right here. Back on step 3, we had this term equaling this, and over here we have the same exact term, which equals this. So, using transitivity, we know that this must equal this. Oh, and what did we have here? It was 1 plus 1, and what did we have here? We had 2. So there we go. Perfect. 1 plus 1 equals 2, written identically to this. Now, as it happens, we can make a very great deal of true statements into theorems, but we're not quite there yet. Using Axiom 2, you can see that you can specify all these values into A, and you will get these theorems. Now, by looking at all these theorems, you can certainly see a pattern, but unfortunately, expressing that is not a theorem, even though you can clearly see it's true. And even worse, it looks almost identical to axiom number 2. So there's obviously a big problem if we can't switch around those, which we know is a property of addition, but so far it's not a property of this symbol. We're going to use a notation that we haven't seen before, but we'll definitely come back to it in later videos. We're going to have x represent a well-formed formula, and then we're going to have a free variable within that, and then when we want to specify the variable, we're going to use what we specify it as, the slash, and then the variable. So one thing we could interpret x as would be this string, and it also, not so coincidentally, is part of this statement. And you know how to specify things, I don't need to go over that. The only way to use this rule we're adding is we need to have this statement and this statement. If both of those things are theorems, then we have this here. So, the two things we need, one of them is for all values a, if we assume that 0 plus a equals a, then we get the successor of a plus 0 equals a. And we also need 0 plus 0 equals 0. So as long as we have the very beginning of this chain, and we also have any link in this chain can be used to infer the next link, then naturally we're going to have what we wanted. Let's see if we can actually do this now. We'll start with Axiom 3, specify out the variables. I'm not going to spend any time doing that. We know we're going to need to do a fantasy rule here, so let's use that from the propositional calculus. So our premise is this thing that we want to start with. We can add s, we'll bring this into the fantasy. Now we have this term equaling both this and this. So we'll use our nice transitivity to get this. And it turns out that's all we needed. We have 0 plus b equals b. And then if we were to substitute the successor of b every time the term b appears, what we would have is this. And look at that, we already have this first part of that complicated new rule that we're using. Now we just need one more thing. And we know that all we need to do to get that is to take Axiom 2 and specify a as 0. Then we get to use our fancy new Induction Rule. Of course, this is using the variable b instead of a. And since I was so very careful to make sure that we got exactly the string we wanted, let's make sure that we can switch it over with a well enough. Now, we're going to take this and we're going to specify the variable b as the variable a. So 0 plus a equals a. So for all values b, one of the values for b could be the value a. Then we're going to use the generalization and add this for all values a. 0 plus a equals a, which is what we wanted to do at the very outset. Well, we certainly went through plenty of paper to get here, but where have we really gotten? I'm sure you're understandably skeptical that we've actually achieved what we set out to do. So maybe by going over the examples and the very small incremental stages we have to go through to get anywhere, hopefully this convinced you that there are at least not going to be any false statements that turn out to be theorems. But the trickier notion of any true statements that aren't theorems, what are we going to do about that one? For now, I'll let you just think about that, and I'll start amassing the next pile of papers. And I'll see you next video. Thank you very much for watching, I appreciate it.